So good day everyone, welcome to another video lecture for today. So this time we are going to discuss derivative of implicit parametric functions and higher derivatives. So for our learning objectives, at the end of the topic, the students will be able to, number one, relate with the definition of implicit function as well as the parametric functions, and then solve problems involving implicit functions and parametric functions, then apply multiple differentiation on implicit and parametric functions. So to start with, we have the derivative of implicit functions. So this is simply to differentiate a function with respect to an independent variable. So meaning we must be aware what is the dependent and the independent variable, and normally we differentiate the independent variable. Say if we have a function of y in terms of x, say y is equal to 2x, or y is equal to 3x plus 7, or another function of y which is equal to x squared plus 2x all over 1 minus 2x. So all of those are in the form of y is equal to the function of x. However, if the equation is not solved for y, like in this form, we have x squared minus 4y is equal to 4, we can say here that y is called the implicit function of x, and x as well is called the implicit function of y. In that sense, we can simplify this equation and solve for y. Hence, we have this equation, y is equal to x squared minus 4 all over 4. And here, y now becomes explicit function of x. But note that in some functions, the dependent variable cannot be explicitly defined. Just like this expression, we have x squared y cubed minus xy is equal to 10. So take note here that y is no longer in terms of x. And it could be very difficult if we are going to solve for y in terms of x. But we must have not to worry about that, because in this case, there is no need to solve for y just to differentiate the equation. We will just have to bear in mind that we derive the function with respect to the independent variable, say x. Hence, we will just apply d over dx to both sides of equation and then solve for dy all over dx. We can further illustrate that through an example. Say we have here number 1, x squared minus 4y is equal to 4. So our task here is to find y prime. So in here, we'll just have to differentiate each of the side, say left hand side and the right hand side of the equation, applying here this d over dx. So remember that x here is the independent variable. So applying this one, we have 2x dx over dx, or the chain rule, minus copy the constant and then differentiate the variable. The variable here is y, hence becomes dy all over dx, and this shall equate to 0. And then we simply substitute that this is 1 and this dy over dx here is y prime, and then solve for y prime. First, 2x will be transposed to the right side, and then we can divide both sides by 4 and solve for y prime. So y prime here is equal to 1/2 of x. Say we have another example, number 2. We have x squared plus y squared is equal to a squared. So again, we just bear in mind that our independent variable here is x. So we're going to find here y prime. So the first term would be the differential of x squared, 2x dx all over dx, plus 2y all over times dy all over dx, and then the constant a squared is equal to 0. Again, this is 1, and that will be y prime. And so we'll obtain this equation, solving for y prime. We transpose 2x to the right sides become negative. Then we can cancel 2 on both sides of the equation. And finally solve for y prime. So for the third problem, again, we're going to find dy all over dx. So x squared becomes 2x times dx all over dx. And then for the second term, we are going to apply the formula on product. We have u dv plus v du. X will be treated as u and y is our v. So u dv plus v du. Then y squared here becomes 2y times dy all over dx. And for the right hand side, we have a constant becomes 0 when differentiated. Again, this is 1, this is y prime, this is 1, and this is y prime. Then we solve for y prime. And then we obtain this equation. Of course, if we are going to solve y prime or after y prime, we're going to group this algebraic equation so that y prime will be isolated in one side of the equation. So obviously, by that, all the expressions with y prime will retain to the left side of the equation, and then all of without y prime will be transposed to the other side of the equation. So we have this as our left side, retaining x y prime and 2y y prime, and then this 2x is transposed from the left side together with y here. So both will be negative, and then y prime will be factored out. So what is left is x plus 2y inside the group. And perhaps we can also factor out negative 1 here, so that the inside term will become 2x plus y. And then finally, we get y prime is equal to negative quantity 2x plus y all over x plus 2y. So let us try another problem. Say we have your x squared plus y cubed is equal to 27. So the first term here is obviously again a product rule wherein we're gonna execute u dv plus v du. So doing that, we have u dv plus v du, and then differentiate this y cube as the second term here. We have 3y squared dy all over dx, and the differential of a constant will be equal to 0 as usual. So we'll come up with the first term, 2xy y prime plus y squared plus 3y squared y prime is equal to 0. So again, we're going to isolate all terms with y prime on one side of the equation. So we're going to transpose y squared to the other side of the equation. So that we'll be having this one, and then factor out y prime. So we have this one. Then solving for y prime, we will be having negative y squared all over 2xy plus 3y squared. But notice here that in the denominator, we can still factor y out so that we can cancel one of the y's here. So doing that, we have y squared all over. We bring out one of the y here. So we'll have an inside function of 2x plus 3y. So in here, obviously, we can cancel one of the y and finally come up with the simplified answer of negative, by the way, this is negative y all over 2x plus 3y. So moving on to the fifth problem. Again, we're going to find here y prime. So the first term, we bring down 1/2 here, and then copy that x, and reduce the exponent by 1. So 1/2 minus 2 over 2 is negative 1/2. And of course, you always apply the chain rule. We also do it on the second term. We reduce the exponent by 1, and then the chain rule, and then differential of constant is equal to 0. We copy here the constant 1/2, then we reciprocate the variable with negative exponent, becomes positive on the denominator. Likewise for the second term, and y prime should be placed at the numerator, this y prime. The right hand side will remain. And of course, we solve for y prime by transposing first this term to the right side, becomes negative. Then we just cross multiply the denominator to the other side, so becomes this. And finally, we have negative square root of y all over square root of x for y prime. So let us have number 6. So again, we will find y prime. So the left portion is obviously in the form of the power formula, wherein we'll just execute nun minus 1 times du. So doing that, we have this expression, and then we apply the chain rule, differentiating now the inner term dx over dx minus y prime, and then the constant times the variable becomes dy all over dx. So in here we have So y prime here is negative x plus y all over negative x minus y plus 1. So moving on, we have this equation. So for the first term, we have 2/3 of x. Then we deduct 1 from that exponent. We also do it on the second term. We have 2/3. We have the y here. And then deduct 1 from the 2/3. And then derive the constant, which will become 0. Again, we copy the constant. Reciprocate x raised to negative 1/3 becomes positive on the denominator. And that, by the way, there shall be dy over dx here as a matter of the chain rule. And also for the first term, we have dx all over dx. So moving on, we do the same for the second term. We bring down y raised to negative 1/3 becomes positive on the denominator. And the y prime should remain at the numerator. And that equates to 0. So we simply cancel 2/3 on the left side of the equation because they are common. We just factor that out. Anyway, our right hand side is 0. So that we can bring out 2/3 here and then divide both sides by 3/2. Then these 2/3 will just be cancelled. So we have that as our first term. And y prime all over 1/3 as our second term equal to 0. Then we transpose, cancel negative, and of course y prime could be easily obtained by simply transposing y 1/3 to the numerator of the right side. So that's it for the 7th problem. We now then proceed to the next topic. We have derivatives of parametric equations, wherein we take off from the definition of parametric, meaning it is within the boundaries or within the parameters. So what does it mean? Simply means that dy dx cannot be solved directly, wherein there is a third function that will certainly connect the two functions. Say if we have x in terms of function of t and y in terms of another function of t, then t function is parametric to x and y functions. So what we do is to derive x in terms of t becomes dx over dt, and our y will be derived in terms of the function t becomes dy over dt as well. Then we just derive both dy over dt and dx over dt. Will just divide the y derived equation to that of the x in terms of t, so that the common parametric function will be just cancelled on our equation, and finally come up with dy all over dx. And that is best explained through examples. Say for the first problem, find dy over dx from the equations. X is equal to t cubed minus 2t plus 1, and y is equal to t squared plus 3t minus 2. Obviously here, the parametric function is t, so we're going to execute d all over dt to both functions. So doing that for the first equation, we have x in terms of t. We have dx over dt, then 3t squared dt over dt minus 2 dt over dt plus 0. Hence, we can simplify the first parametric equation to 3t squared minus 2. We also derive the second equation in terms of t. We have dy over dt is equal to the first term, 2t times dt over dt plus 3 times dt over dt less 0. So dy over dt will be simplified to 2t plus 3. Now that we have obtained this, we simply say that dy over dx is equal to 2t plus 3 all over 3t squared plus 2. By the way, let me mention here that usually the third parametric function, t, could be in terms of time. Okay, so this is something that say x, if we refer to a distance, this is what we call a relative rates. So relative rates could be the most topic that parametric equations can be applied, such as velocity acceleration or angular acceleration, etc. So another example, we have another equation, x and y in terms of t. We are going to find dy over dx or y prime. So again, we'll just have to execute d over dt here on both x functions and y function. Hence, dx over dt is simply equal to dt over dt, or that equates to 1. Then dy over dt is simply 2t dt over dt, or simply equal to 2t. And in here, you can see that dy over dx is 2t all over 1, or that is equal to 2t. So let us have here number 3. Once again, we are concerned with dy over dx, and obviously u is our parametric functions. So we're gonna execute here d over du. First, for the x function, we have dx over du, and here we have quotient rule. So simply quotient rule is v du minus u dv all over v squared. Our v is 1 plus u. Differential of u is du over du, or 1, minus u differential of v is 0 minus du over plus du over du all over v squared, or 1 plus u squared. So we can simplify the equation into 1 plus u minus u over 1 plus u quantity squared. Obviously, u is cancelled, so we come up with that equation. We do the same for the second function, which is y. So we have dy over du. Once again, this is in the form of quotient. V du, which is 2u du over du, minus u, which is u squared, differential of v, which is 0 plus du over du. We divide that by the square of our denominator. So dy over du can be simplified by distributing first 2u here to the quantity 1 plus u, so becomes 2u plus 2u squared less u squared all over 1 plus u quantity squared. So we simplify by subtracting u squared to the 2u squared, becomes u squared plus 2u all over 1 plus u squared. And so finally, dy over dx is simply dividing this term to this term. Say that is for dy over du, and that is dx over du. So that denominator here is cancelled. Hence, we have here u squared plus 2u. Say for the fourth problem, we have x is equal to t squared all over 2, and y is equal to y minus t. So obviously, x and y is within a parametric function of t, and thus we apply or execute d over dt. So the function of x with respect to t, we have v du minus u dv all over the square of the denominator. So we have dx over dt, considering that this is equal to 0, and the 4 here will just be cancelled. Therefore, dx over dt will just be equal to t. For our y function, we have dy over dt, this is 0, less dt over dt, which is obviously equal to 1. Therefore, dy over dx is negative 1 all over t. So that completes our problem in parametric equations. So moving on to the next topic, we have here higher derivatives. So previously we have dealt with general form, the implicit form, and the parametric form, just to arrive with dy over dx known as y prime, which is known as the slope of the tangent line. Why is it that this is a slope of the tangent line? Because it is the difference of the vertical to that of the horizontal. Remember that the function of tangent is opposite over adjacent. And if we are after the horizontal angle, our opposite is the y, or the difference in y, and the adjacent is the difference in x. So that dy over dx is actually y prime. So going back with the topic proper, this is just a series of derivatives of this y prime. So we will just make series of derivations. Of course, if we are going to derive y, becomes dy over dx, or that is y prime. And deriving dy over dx, or the y prime, becomes y double prime. And deriving y double prime becomes y triple prime, and so on. So this can be applied on either general form, implicit form, or parametric form, and it can be best illustrated in examples. So we have find the fourth derivative of dy over dx is equal to 12x cubed minus 6x squared. So this is actually y prime. Deriving this again becomes y double prime. So we have the first term and then the second term. We have 36x squared minus 12x. So this will be our y double prime. Deriving y double prime with respect to x becomes y triple prime. We have here the first term. We bring down 2, reduce 1, and the second term is 12 times dx over dx. So y triple prime is equal to 72x minus 12. And then finally, we derive that again. It becomes now the fourth derivative, which is simply equal to 72. So this is the answer. So we try this one to implicit form. So find y double prime of x squared plus y squared is equal to a squared. We execute the first derivative. We have 2x times dx over dx plus 2y times dy over dx, or y prime. That would equate to 0. Solving for y prime, we have negative 2x all over 2y, or negative x all over y. Then we derive it again with respect to x. This becomes y double prime, and we'll just execute this one, v du minus u dv all over v squared. We place first here the negative sign, then execute this, say v du minus u dv all over the square of our denominator. So observe that y prime here is present in our equation. So no problem with that. We'll just have to replace it by its defined function here. So y prime here is replaced by negative x all over y. So we simplify the numerator. So x will be combined to that fraction here. So that becomes x squared all over y. So perhaps you can merge this into its LCD. So the LCD for that numerator is y. So that the first term becomes y squared. And the second term is just the same, x squared. So we come up with this equation. So it can be written as this one. And we should remember to place negative here. And note that this is positive signs because of this combination. Negative x times negative x inside becomes positive. So with that, we can now simplify this to negative y squared plus x squared all over y cubed. So notice here that y squared plus x squared is actually a squared from the original equation. X squared plus y squared is equal to a squared. So finally, this shall equate to negative a squared all over y cubed. So this is an example for implicit form. So here we're going to find the second derivative of the parametric equation. So we have x is equal to t squared plus 1, and then y is equal to 2t plus 1. Obviously, x and y is within the parameters of t. Hence, we are going to execute d over dt. So doing that for the first equation, we have dx over dt is equal to 2t times 1 plus 0. Similarly, for the second equation, we have dy all over dt is equal to 2 times dt over dt, or equal to 1. Then dy over dx is equal to y prime is equal to 2 all over 2t, or equal to 1 all over t, considering that 2 here is cancelled. And then from here, we derive it again with respect to x, becomes y double prime. So this is in the form of v du minus u dv all over v squared. V du is obviously t times 0 minus u times dt all over dt. So here we must be careful that the second term here is negative u is 1 times differential of v. What is v, or differential of v with respect to what? So we should question ourselves with respect to what. So y prime here shall be derived with respect to x, so that it will become y double prime. So therefore, we should note that this is not equal to 1. Instead, it should be the differential of t with respect to x all over the square of the denominator, so t squared. So in here you can notice that dt all over dx here is found in the equation. So where shall we get the value? So notice that dx over dt here is equivalent to 2t. So this is just the reciprocal of this function. So therefore, you can just say that dt over dx is equivalent to 1 over 2t. So now we can simplify everything here. So this is our numerator, negative 1 over 2t times 1 over t squared. So finally, y double prime will yield to negative 1 all over 2t cubed. So this is how to do it for the parametric form. So I guess you will be sharpened if you will solve parametric form, general form, and implicit form for higher derivatives. So please stand by for our quiz and activity for the day. So thank you for listening and good day.